Welcome back to The Explainer. So today, we're tackling a topic that honestly tends to make a lot of developers just a little bit nervous: linker scripts and command files. By the end of this explainer, we're going to totally demystify these files so you can modify them for your own systems with absolute confidence. Let's step through this together, shall we?
Right off the bat, I want you to think about this absolutely fundamental question. How does a linker know where memory actually is? I mean, we all know the compiler turns your beautiful readable source code into object files, right? And we know the linker takes those object files and libraries to produce the final executable. But there's a massive gap there. Where does the code actually go? Where does the data live in the physical hardware? The linker isn't magic, you guys. It doesn't just inherently know the physical layout of your specific microcontroller's memory. It desperately needs a blueprint.
And well, that blueprint is often what makes us panic. If you've ever opened a default linker script that came with your IDE, it probably looked a whole lot like this. It can be incredibly intimidating. Just a wall of cryptic syntax, strange symbols, and completely arbitrary rules. Even the comments in the source material we're looking at today literally ask, why is this here? So, your panic? It's completely validated. But let's translate this ancient script into plain English.
Here is our roadmap for today. 1. The linker script mystery. 2. Mapping the memory. 3. Decoding the jargon. And 4. Writing the rules.
Now, our source material today comes straight from George Mock, a software developer over at Texas Instruments. With 32 years of experience working directly on C and C++ compilers, assemblers, and linkers, his insights offer us a truly practical masterclass on how these tools actually function under the hood.
Section 1. The linker script mystery. From confusion to clarity.
At its core, a linker script, which, by the way, is the exact same thing as what Texas Instruments calls a linker command file, is just a text file. Yep, that's it. It's a standard text file exactly like any other source file you write. Its entire job is to tell the linker the layout of the memory, how to combine your code and data together, and exactly where to put it in that memory. When you invoke the linker using GCC, you usually specify this file with the T option. With TI tools, you often don't even need an option. But regardless of the toolchain, it's just a simple text blueprint.
Moving on to Section 2, Mapping the Memory, the Foundation.
Okay, let's dive right into this. A linker script essentially relies on two massive foundational pillars: the memory command and the sections command. The memory command assigns names to specific physical regions of memory. Think of it as defining the actual map. The sections command, on the other hand, does two things at once. It forms output sections from your input sections, and then it allocates those output sections into the memory regions you just defined. It's basically the traffic cop directing the actual code onto the map.
What's really interesting here is how simple the memory command actually is once you isolate it. All it's doing is taking raw physical hardware addresses, like, origin 0x0041C00000, and assigning them friendly human-readable names like MCU reserved or OCMC RAM. It just specifies the starting address and the length of the region. By setting this up first, the rest of your script doesn't have to deal with ugly hexadecimal addresses anymore. It can just say, hey, put this in the OCMC RAM.
And this brilliantly illustrates the sections command. To really visualize this, picture a factory floor plan. Up at the very top, you have your raw materials, the object files and libraries generated by our compiler. Inside those files are the input sections, the specific pieces of code and data. The sections command takes those little input sections, groups them together based on your rules, and builds the finished product, the output sections, labeled here as OS1, OS2, and so on. Finally, it drops those assembled output sections right into the memory regions, M1, M2, M3, that you just named using your memory command.
Section 3, Decoding the Jargon, the Building Blocks.
First up is the object file. As we just saw at the top of our factory floor, an object file is essentially just a collection of input sections. When your compiler finishes with a C file, it hands over an object file. These can be presented directly to the linker, or they can come bundled up inside a library, typically ending in .obj or .lib. They're essentially the shipping containers arriving at our factory.
Now, if we pop open those shipping containers, we find the input sections. An input section is one specific section stripped out from one single object file. It contains either your executable code or your data. And if it's data, it might be initialized with a specific value, or it might be uninitialized. Think of these as the individual widgets on our assembly line.
Next is the output section. This is the finished boxed-up product. It's a collection of one or more of those input sections, and it's formed entirely by the rules you write in the sections command. The linker bundles the widgets into the output section, making them perfectly ready to be placed permanently onto the shelf.
So, the absolutely crucial point here is understanding how different types of contents require different destinations. The .text section contains your executable code which needs to be initialized. The .data section contains initialized data that will actually change during execution. The .bss section is for global variables that are uninitialized, so they just get zero filled. And .row data is your read-only initialized data, constants that literally never change. Because they behave so differently, they have to go to different memory locations. Read-only data and code typically go to flash memory, while variables that change need to be placed in RAM.
Now, I want to offer you a huge moment of relief. You're going to see sections like .comment, .note, or maybe sections starting with .stabs. Listen, unless you read debugger symbols for fun on the weekends, just ignore them. They are not loaded to your target hardware. Just leave them alone and don't let them clutter your process.
Section 4. Writing the rules. Syntax evolution.
Let's move to and see how this syntax actually builds and evolves, starting from the most verbose way to write a rule, all the way down to the elegant shorthand you'll actually see in practice. Step 1, you could explicitly list every single file. You could write file1.o.text, then file2.o.text, telling the linker to grab the text sections from those specific files. But wow, that's tedious. So, step 2, we use a wildcard. The **star.text simply says grab the .text input section from all the object files. In step 3, we put it into an output section block. We name the output section .text, put our wildcard rule inside the curly braces, and use the greater than sign to shoot it directly into the flash memory region. Finally, step 4, the ultimate shorthand. Because the input section name and output section name are exactly the same, modern linkers let you just write .text greater than flash. It means the exact same thing as step 3, just beautifully simplified.
And just like that, the mystery is solved. You now understand the map, the factory floor, the inputs, and the outputs. So I leave you with this final challenge. Can you open your IDE's default linker script right now, look past the debugger sections, find the sections command, and trace exactly where your .text section goes in hardware? I bet you can for sure. Thank you for joining me on this explainer. Keep learning, keep exploring, and I'll see you in the next one.